joining us again. I think you've visited us numerous times at LIDS in the past. Mor Harchol-Balter is a professor of computer science at CMU. She received her PhD from UC Berkeley, and after her PhD, she actually spent 3 years with us at MIT as a postdoc. Mor is a very well known researcher in the scheduling and operation research domain. She is an author of a wonderful textbook on performance analysis and design of computer systems. She's also a great speaker, and we love to see her in person, but unfortunately we have to do this via Zoom this year, but I'm sure she'll do a great job. Mor, thank you for joining us.
Thank you, Eitan, for having me. So, people, I give these kind of technical talks, but I'm still expecting a lot of interaction. So please interact, especially when I ask questions. Please volunteer an answer. Don't be afraid to just call it out. Okay. So, I'm going to be talking about a new way of thinking about scheduling that is going to allow us to analyze a whole bunch of scheduling policies that we were never able to analyze before. So a way of really expanding the number of scheduling policies we can analyze. So this is joint work with my student Zeev Scully. You might know him. He was an undergrad at MIT, and he's really the brains behind this whole operation. And for his work on SOAP, which is what I'm going to talk about, okay, really like soap, like a bar soap. For his work on SOAP, he was an APS finalist. And then he just kept writing papers related to SOAP. He kept building on SOAP, and then he kept winning more awards as he kept building on SOAP. And he's going to be on the job market next year. So, so just remember, this guy's going to be around. And this is also joint work with my wonderful colleague, Alan Schellerwolf. So, okay, let's get started. So I've always loved scheduling, okay? When I first started at MIT, when I was doing my postdoc, I was very interested in this shortest remaining processing time, which is a policy that gives bias towards the job with a shorter remaining time, and whether it's actually still fair to the big jobs. And it turns out it is. So you can ask me about that later. I also was very interested in this idea of separating small jobs from big jobs and creating the separation. I call it size interval task assignment. And then later, I became interested in scheduling from the perspective of saving power. When should you turn servers off? When should you turn them on? You know, stuff like that to try to save power. And I've worked in many areas of scheduling. Recently, I'm interested in parallel job scheduling, but it's another story, okay? But in my textbook, so I have this textbook, I actually devote a whole bunch of chapters to scheduling. So every scheduling policy is a different chapter. So there's like chapter 28, 29, 30. And because scheduling is so difficult, you really need a full chapter to explain how to analyze each policy. But what's sad is that even at the end of this, I realized there's really very few scheduling policies that we know how to analyze. If we want the mean response time of some scheduling policy, there are very few that we can do. And so the purpose of this talk is to try to grow that class. But before I start, I want to make sure everybody's on the same page. So I like to start my talks with a tutorial. And I'm going to give you a little mini tutorial on scheduling so everybody understands what we're talking about. Okay? So sorry if this is a little boring. So this is a queue, and imagine that there are online arrivals coming in. These are the jobs that are coming in. And when you see a job, you can see that some jobs are big. That means they have a large size, large service requirement, and some are small. And typically when we look at jobs, we don't know the size of a job. We don't know which one is big and which one is small. What we do know is how much service the job has received so far. This is the age. So age here is not the time the job has been waiting, okay? So it's not age of information, okay? Age here is the amount of service the job has received so far. It's how much running time it has gotten so far. And then the rest of the job, we think about the remaining size. This is how much service is left to be done. And the sum of the age and the remaining size is the total size. So again, The age is available to us because we see jobs running and we know how much processing we've given to each job. So we know a job's age, but we might not know its size, okay? And within this world, I'll be interested in talking about response times, which is the time from when a job arrives until it completes. This is also the sojourn time. And I'm going to call this response time T, and you're going to hear me talk a lot about T, okay, the response time and minimizing the response time. And we'll be looking at different scheduling policies. The scheduling policy just says at every moment in time, which job am I going to run? And I'm assuming that I can preempt jobs and resume jobs at no cost. So I can stop and restart, no cost in the scheduling policy. And this kind of model occurs all over computer systems. The easiest example for you to think of in your brain probably is a CPU run queue. So just imagine these are the jobs that are ready to run on the run queue, and now we're scheduling them in our CPU. But there are many other examples. And for the purpose of this talk, I'm going to be sticking to an MG1. So all that means is the arrival process is going to be a Poisson process. I'm going to use lambda to denote the number of jobs per second. And the sizes of these jobs are going to be drawn from a job size distribution. So I'm assuming that I know this job size distribution because I've been watching jobs over time. And so I have a sense of what the job size distribution looks like. And they're drawn IID from this distribution. And the only other real piece of notation I will use is this notion of load, which is the fraction of time a server is busy. And we all know that that's the arrival rate, lambda jobs per second, times the mean service requirement or mean size, E of X. And this load, I'm assuming, is less than 1. And within this context now, I want to talk about scheduling. Okay, so I'm assuming there are no questions, but please wave at me if you're already confused. Okay, all right, so I have a question for you. Okay, suppose you know the sizes of the jobs, so I know exactly who's small and who's big in terms of the service needs. Which scheduling policy should I use to minimize E of T? E of T is the mean response time. Remember, T is response time. Which scheduling policy should I use? Please, somebody? Gonna have to call on somebody. Anyone? Sandeep, would you like to answer?
I don't know, schedule the ones that have a shorter service time first.
See, these MIT students, they always know. Okay, so SRPT is the answer, shortest remaining processing time. So at every moment in time, you always want to work on the job that has the least remaining processing time left. Okay, this is very much what we do on our own desk. Like I'm always looking for like, what can I finish quickly so I can feel good at having done something? But it turns out that this kind of policy, SRPT, also minimizes mean response time. And that's really nice. And if you want to know how good it is, you can open up, for instance, my textbook. It has a picture of mean response time as a function of the load. Remember, load is the fraction of time the server is busy. And you can see different scheduling policies, the few that we can analyze. So for instance, you can see first come, first serve. That's one scheduling policy. You can see processor sharing, which time shares between jobs. And you can see that it's much better than first come, first serve for mean response time. You can see a policy called foreground background. This is a policy that always picks to run the job with the lowest age. Remember, age is how much service the job's received so far. So foreground background chooses to run the job with the lowest age. Sometimes this is better than processor sharing, sometimes it's worse. This is just one example, okay? There's preemptive shortest job first, which runs the job with the shortest size, shortest inherent size. And then there's SRPT, which runs the job which always has the shortest remaining time. So maybe my original size was big, but my remaining time is very little. And so I would have preference here in SRPT. And as we can see, SRPT is definitely the way to go. Okay, so Sandeep is right. You want to do SRPT, okay? So then you might ask yourself, well, is SRPT used all over the place because it's so amazing, like it must be used in a lot of systems. But when you actually look at systems, there's a systems paper I wrote back in 2003. And then there's one recently from Stanford, 2018, okay? John Osterhout has a group working on some things with SRPT, but basically you don't see much SRPT in computer systems. And the question is, if SRPT is so awesome, why isn't it being used all the time? Like why don't we use policies like the good ones, like SRPT or preemptive shortest job first? Why aren't we using these great policies? Anybody? Please unmute, speak. You don't want me to have to come
I wonder, like, what if we have to use a non-preemptive scheduling?
Yes. So I will talk about that a lot actually in this talk. Like sometimes you don't have preemption, or you have only a limited amount of preemption. Or you have, okay, so yeah, so sometimes you're limited in the policies that you can use for that reason, and then you can't do SRPT. Is there any other reason why people don't choose to use these kind of size-based policies?
Sometimes you don't know the size.
Yeah, sometimes you just don't know the size. And it turns out that for computer systems, you often don't know the size of a job until you run it. As you run it, you see its age goes up, and eventually it stops. And then you're like, oh, that was the size. But you don't know it in advance, okay? So what if you don't know the job size? How are you going to optimally reduce mean response time? How are you going to schedule? So let me be very clear. So you have a queue, and you know the age of every job. You know how much service it has received so far. You know its age, okay? The service it's received so far. And you know the overall job size distribution. You know the whole distribution because you've been watching jobs over time. So you have the age, and you know the job size distribution, and you'd like to do shortest remaining processing time, but you don't know the job size. What could you do? Question. Somebody, please.
You could decide a threshold and then stop serving the job if it takes more than that time.
Right, okay, so you could kind of loosely base it on some kind of threshold, which is somehow taking into account the job size distribution in some way. But maybe you could use the job size distribution to actually compute which job is going to, in expectation, maybe have the shortest remaining size, right? So maybe you could go one step further than what you're suggesting. Okay, so what would that be? So explain that to me, anybody? No? Okay, I'm gonna make you answer more questions. This is the easy stuff now. Okay, so what I'm proposing is maybe you would want to use something like shortest expected remaining processing time. Okay, so you're using the distribution and you're running the job with the least expected time. Okay, so what does that mean? I just want to make sure everybody's very clear because I don't want to lose anybody at this point. Okay, so let's look at an example. Suppose your job size distribution is very, very simple. Jobs are either of size 1 or 6 or 14, and they're equally likely to be any of those sizes. Okay, and now at every moment in time, I don't know what the size of a job is, okay? I don't know when a job comes in, whether it's a 1, a 6, or a 14. But at every moment in time, I want to run the job with the shortest expected remaining time. So you can imagine a graph like this that has expected remaining size here, the expected remaining size on this axis, and the age, which is the only thing you know about a job, on this axis. And R of A, this is the rank of a job of size A, is just its expected remaining size. So when a job comes in, what is its expected remaining size? When a job has age 0, what is its expected remaining size? It's the average of 1 and 6 and 14. Please, somebody.
7.
Yes. 7. All right, so its expected remaining size is 7. So its rank at the beginning is 7, and then the rank starts to go down, which is good. That means it has shorter remaining processing time. What happens when the job passes 1 second? So it's already taken 1 second, and it seems to be continuing, okay? So now it's not of size 1. What is its expected remaining time? So here it passed 1 second, so either it has 5 seconds left with probability 1/2, or it has 13 seconds left with probability 1/2. So what's its expected remaining time now? Yes?
Was 9.
9.
Anybody?
9.
9, thank you. Okay, so it goes up to 9. So the expected remaining time actually went up, okay? Now the job runs and runs and runs, and its remaining time goes down until just after it passes 6. And if it passes 6, then we know its remaining time, and it goes up to 8, okay? And then it goes down. So you can see its expected remaining time changes over time, okay? Now, what this policy says is that every moment in time, you want to run the job with the lowest rank, okay? The rank here, remember, is the expected remaining size. And I want to pick the job with the lowest rank. So if I have a job that has age 3, this is its rank. And if I have a job that has age 12, this is its rank. And I want to pick the better of this and this, meaning the lower one. And that's how this policy works. Okay, so everybody understand shortest expected remaining processing time. You can imagine that you can compute this, okay? Okay, so is SERPT the optimal thing to do if you don't know size and you do have preemption? So you can preempt jobs, but you don't know the size. But you know the job size distribution, okay? And you know the ages of jobs. Should you do SERPT? Anybody want to tell me? Do people want to vote? Do you want to tell me yes or no? How many yeses do I have? You can hit the yes button. You all know how to do this. You can hit the yes button if you say yes. You can hit the no button if you want to say no. Okay, so far it's a tie between yes and no. All right, okay, no further respondents. Okay, so the answer is no. SERPT is not, okay, the optimal thing to do. It's very good, by the way. I've been writing papers on how good it is. But okay, so what is the right thing to do? So instead of telling you, I'm gonna have you try to figure it out, okay? So remember here, we had this rank, R of A, and the rank was the expected remaining time. Remember, X is our job size. So this is the remaining time given my job is at least A. So given my age is A. So given my age is A, what's the expected remaining size of a job? And this is what it looked like, okay? Now consider a job whose age is 1. Okay, or maybe just before its age is 1. Its rank according to this is 6, okay? But the truth is, suppose you had a job and it was almost age 1, like it was some little delta away from being age 1, a tiny, tiny delta away from being age 1. So it's almost age 1. Should you invest that delta in just running the job? Because it might end. Right? I mean, it might complete like that, right? So doesn't it seem like you should maybe invest? Do people believe you should invest or not? Give me a yes if you believe you should invest, since nobody wants to talk to me. Okay, nobody wants to invest either. Okay, yes, some people want to invest, okay? So the idea is if its age is very, very close to 1, or its age is very, very close to 6, we should just run that job because it's delta away from being that being 1, and then we can learn some very important information. Maybe the job will finish. So this policy has a different rank function. It looks more complicated. It's called the Gittins policy, Gittins Index policy. And its rank function is a little more complicated. You'll see that it still has this notion of the expected remaining size of a job. But now there is this other parameter delta, which says if the probability that I'm going to finish within delta is high, if there's a high probability that I'm going to finish within delta, then that drops my rank, which means I should really run that job. And that's what causes the rank to go down like this, down to 0, making this job very desirable, okay, when it's very close to being at one of these points. Okay, so I'm not going to spend a long time on this Gittins rank. I'm just going to let you know that this Gittins index, this policy is optimal, okay? For the MG1Q, this is the optimal scheduling policy, is to use this rank function. So if you don't know the size of a job, this is what you want to do. You want to use this policy. What's important for the purposes of this talk is that this policy has a rank, and so we can choose at every moment in time which job to run. As a function of the job's age, we can see its rank, and then we always run the job with the lowest rank. That's what we do, okay? So it's a different policy, a different rank function, but again, it's a rank function. All right. So the Gittins policy, as I said, turns out to be optimal, okay, for mean response time. But the question that I have is, what is its mean response time? Like, do I want to bother with this complicated Gittins policy? Maybe I want to do SERPT. Okay. So it turns out that the mean response time under Gittins was unknown until 2018, until this paper, until the SOAP work. Furthermore, the mean response time under SERPT, remember the other policy, shortest expected remaining processing time, that also was unknown until the SOAP work. Furthermore, the mean response time under any policy whose rank function is non-monotonic, whose rank function goes up and down. Remember how SERPT and Gittins had rank functions that go up and down? Any policy with a rank function that's non-monotonic like that, we didn't understand its mean response time until the SOAP work. And so what I'm going to do today is I'm going to answer all these questions. I'm going to show you how you can actually analyze it, and we're going to go step by step. Okay, so first let me just define SOAP. So SOAP stands for Scheduling Ordered by Age-Based Priority. And a SOAP policy, okay, a SOAP policy is any policy that you can express via a rank function. So it's any policy where you can describe the whole policy by rank as a function of age. So you saw how before we had these nice graphs for rank as a function of age for SERPT or for Gittins. Any policy that can be described as rank as a function of age is a SOAP policy. Now we're also allowed to use the job size or the job's class. Like I'm priority class 1 or priority class 2, we're allowed to use that. So you can have a different rank function for different classes or for different sizes, okay? But basically it's a rank as a function of age. I will give you a lot of examples, okay? And the idea is that you always serve the job of the lowest rank. And if 2 jobs have the same rank, then we use first come, first serve tie breaking. So if you have a scheduling policy and you can define it as rank as a function of age, where you always serve the job of the lowest rank, then, and you can take into account size or class if you want, then it's a SOAP policy. And then what I'm going to tell you is that we can analyze it. Okay, so let's look at some examples because I know this is abstract. All right, so consider the FB policy. If you remember, FB is a policy that always biases towards the job with the lowest age. So if you're brand new, like you haven't started running yet, then you have like the best rank, you're the lowest rank. But if you've been running for a long time, okay, if you've already received a lot of service, then we're less excited about you, okay? And so then your rank becomes worse. So here's the rank function, R of A, this is your age, and remember that lower rank is better. So for FB, I want you to turn your video on and show me with your hand, what does the rank function look like? As the job ages, what happens to its rank? Anybody want to tell me? Does it go like this? Does it go like that? Does it go like this? What does it do? Good, thank you. Okay, the rank goes straight up. Thank you, John. All right, feel free to like just draw on my slides. Awesome. So this is the rank function for FB, okay? Now, that means we can analyze it because it's a SO policy, okay? Here's another SO policy, SRPT. So again, I want the rank of a job. Let's assume that the job has some size, like 5. What happens to its rank as it ages? So remember, we're ranking it based on its remaining processing time. What happens to its rank? Does it go like this, like this, like this? What does it do? Anybody? Okay, so the answer is like this. Okay, this is its rank. The rank goes down. Okay, this is for a job of a job of size 5, but a job of size 3 will have this rank function because its rank will go down starting at 3. A job of size 1 will have this rank function. So there are many rank functions, and at every moment in time, I look at all the jobs and I pick the job at the moment based on its age that has the lowest rank, and that's the job I run. And that's the definition of SRPT. So an easy one is like first come, first serve. This just has a flat rank function. All the jobs have the same rank because we have first come, first serve tie breaking anyway. So this is very trivial, okay? So I can keep going with policies we know. They're all very simple rank functions, okay? But there are also SO policies that at least previously had unknown analysis, okay? And so for instance, SERPT can be described as rank as a function of age. This is the shortest expected remaining time. And you'll notice that its rank function is non-monotonic. It goes up and down. Likewise, the Gittins policy also has rank as a function of age, and its rank function is non-monotonic. So for these non-monotonic policies, now no problem, okay? We can analyze them, and we can analyze multiple classes of jobs, each running these policies. Okay, here's another example of something that might be interesting to you. At least it was interesting to me. It was one of the things that motivated SOAP, was this idea of a discretized policy. So remember how we had FB, the FB policy, and remember how the way FB works is when the job gets older, its rank gets worse and worse and worse and worse, okay? This is the one that John drew, okay? The rank gets worse and worse as the job gets older. But let's suppose that you're only allowed to preempt the job at non-integer times. At integer times. Like when the job reaches these integer valued ages, that's when you're allowed to preempt it. But in between these integer valued ages, you're not allowed to preempt the job. So like you can think of a job with checkpointing where you're only allowed to preempt it at certain checkpoints or something, okay? So in between these points, we would like to be able to specify that you can't preempt a job. So in order to do that, we're going to give it a rank, which is down here. So when the job first comes in, it has rank 0, which seems pretty good, but that job still can't preempt a job whose age is way out here if that job is in between its checkpoints, okay? Now, once this job finally does get to run, it runs and nobody can preempt it. But then it goes up here and now its rank is worse and a new job coming in could preempt it, okay? So this is how this kind of thing works. And as you'll notice, this rank function is non-monotonic, okay? But now it's analyzable. Okay, here's another example. So this is an example that I was thinking about because my son was working at Amazon, and he was telling that about the humans and the robots and the jobs that they have there. So this is something that I never thought I would be able to analyze, but it turns out to be easy once you see what the rank function is. And I'll give that to you at the end of the talk. Okay, so imagine that there are these humans, and humans have priority 1. Robots, on the other hand, have priority 2, okay? And humans, being humans, are like, I don't want to be preempted, and you have to work first come, first serve, because they're kind of very fussy, these humans, okay? And for the humans, we don't know the size. But for the robots, on the other hand, you can preempt them as much as you want. They don't have any feelings. We know the size of the job, and we might as well run them SRPT, because why not? That's the right scheduling policy. So now we'd like to analyze a policy that has these 2 classes, okay? But maybe we even want to add a twist. And the twist is like, suppose the remaining size on the robot is very, very little. It has very little left to do, okay? Then maybe at that point, we should be able to give the robot, which is class 2, priority over the human, assuming the human hasn't started yet. Because if the human has started, you don't want to preempt the human, okay? So this is an example of a policy that you can describe via the rank function. And so boom, it's analyzable. Okay, so our result is the first analysis of all SOAP policies. Given any rank function, I will give you a closed form expression for the mean and transform of the response time, including conditional response time. Okay. So what I'm going to do in the rest of this talk is show you how this whole thing works. And I'm going to run through as much as I can, and it will really help if you answer the questions. Okay, so we can go run through it faster. All right, so I want to explain why, first of all, this analysis is difficult, why the non-monotonicity is such an issue. So when you do scheduling analysis, people often think about something called the tag job. So the idea is you have an arbitrary job, like job J, okay, I'm going to be job J, and I walk into the system, okay, we're going to tag me, and we're going to look at what I experience. So I walk into the system and I see these other jobs, but only some of them are relevant to me, okay, because only some of them are my rank might be better than some of them. So only some of them are relevant to me. And then I have to wait for all that relevant work to clear out. And then finally I get to run, and then I start to run, and then maybe I get interrupted by other jobs that have better rank than I do, okay? So the way that I explain this when I teach the stuff is I say, there's this notion of relevant jobs, and when I walk in, I'm job J, so I'm this green job, and I basically I have a certain rank, okay? Remember, lower rank is better, and I only see the jobs that are relevant to me. So I walk in, and it's kind of like I put on these special glasses, and I call them my transformer glasses. And when I put them on, what happens is, through these glasses, I only see the jobs that are relevant to me, which is very nice because now I can start thinking about how they're going to affect me, okay? The problem is that now my rank function is non-monotonic, so my own rank is going up and down as I age. So as I age and as I run, what is relevant to me is changing all the time. Furthermore, everybody else's ranks are also going up and down as they age. And this is why these kinds of policies have been so hard to analyze. Okay, but we're going to do it here today. Any questions? Okay, all right. So what I'm going to do for the remainder of the talk is I'm going to do one little example like this SERPT. In general, we can handle much more complicated examples, but I'm going to stick with this one because I feel like you've already seen it. You've seen a little bit of it, okay? So here, remember the rank, this rank of a job is its expected remaining processing time. It starts out with an expected remaining processing time of 7, and then its remaining processing time can go up and down. And what I'm going to do is I'm going to ask you how do we figure out the response time of a job J, where as a warm-up, we're going to assume the job J arrives into a totally empty system. So I'm job J, and I come in like this, and I'm coming into a completely empty system, and so I am just going to start running right away. And we need to figure out my response time. So here I am, I'm ready to run. First, tell me, what is my size? Who can tell me what's my size? Please answer. Or chat. If you don't want to answer. What's my size? Anybody? Okay, it's a trick question. Does anybody notice it's a trick question? I don't know my size. My size is maybe 1, and it's maybe 6, and it's maybe 14, okay? I don't know what my size is. So now I'm going to start running, and as I run, these other jobs are gonna come. And so remember, I'm running, I'm starting to go down like this, okay? I'm running, okay? So the question that I'm gonna have for you is, for every possible case of what my size is, my size might be 1 or 6 or 14, I'm going to ask you which arrivals contribute to me and how much do they contribute? Because I'm just going to start running, and so my response time should be my size except for the ones who bother me. So I want to figure out who's going to bother me. So if I'm of size 1, I'm going to wait here. I'm going to ask you, I'm of size 1, I'm going to start running just right now. Which arrivals are going to interrupt me? What are the arrivals that are going to interrupt me? Please show me your video and answer the question and unmute. None. Excellent. Okay. So nobody's going to interrupt me because my rank is just going down and everybody else is rank 7. So no one is going to interrupt me. And how much do they interrupt me? They don't. Okay. They just don't interrupt me. Okay. Now a harder question. My job size is 6. So I'm going to go down like this. I'm going to go up and I'm going to go down. Okay. My job size is 6. Some of the arrivals are going to bother me. Okay. Some of the arrivals are going to contribute to my response time. Which arrivals are going to contribute to my response time? Which ones? Does anybody want to tell me? Please speak.
It seems that all arrivals, they're going to all have mean time of 7, right? So if you are not beyond that point, then they're going to all interrupt you, right? As soon as they arrive.
So when I'm down here, for instance, like down here, like this, my rank is better than 7 and they have rank 7. At some point, my rank will be high up here, and then my rank starts to get better and better and better, at some point dropping below 7. When these new arrivals come in, they have rank 7. My question is, which of these arrivals is going to contribute to my response time? Like if I'm down here and my rank is here, so say my age is 5, is an arrival during that time going to contribute to my response time? If an arrival comes in when my age is 5, remember my final age is going to be 6, is the arrival going to contribute to me? Answer?
No.
No, it's not, okay? The arrival is not going to contribute to me. So my question is, which arrivals are going to contribute to me? So for instance, how about the arrivals here between 1 and 3? So when I'm of age between 1 and 3, will these arrivals, will the arrivals now be contributing to me? Yes.
Yes.
And how much will they contribute? Will they contribute their entire size to me? How much will they contribute?
1.
They'll only contribute 1 because they'll only do this, and then their rank will go up. So they'll only contribute 1, and this is if they arrive between 1 and 3. Now remember, my size is 6. Will any other arrivals bother me? So we said that the arrivals that are bothering me are coming in between my age being 1 and 3. Are there any other arrivals that will bother me?
No.
Okay, so that is incorrect. Think again. This is a hard question. Will any other arrivals bother me? Okay, this is really hard.
I think there can be arrivals when your age is smaller than 1, but it's just stuck in there.
Aha, excellent. Okay, so your name is Jinjae, is that right? I don't know how to pronounce
Right, it's Shinja.
Okay, say it again.
Shinja.
Singa. Okay, so that was totally right, okay? So imagine that an arrival comes here when I'm of age between 0 and 1. That arrival that entered when I'm between age 0 and 1 should not be bothering me, right? Because my rank is better. But it will bother me because it will sit there in the queue like this, unable to move, okay? Just sit. And then when my rank goes up here, as it inevitably will, then that arrival would be like, I'm coming on in, and it will come in and it will start bothering me, okay? So actually all the arrivals during this whole time will bother me, okay? So the answer is any arrival when my age is between 0 and 3, and they will bother me by 1 unit of contribution. So again, these arrivals that are coming in here between 0 and 1, okay, those arrivals are unable to move. They're just sitting here like this until my rank goes up, which it surely will, and then they all get to do their 1 unit of work, okay? But only 1 unit because then their rank goes up. Next question. Suppose my size is 14. Now my rank, so I start running, I go down, I go up, I go down, I go up, I go down. Which arrivals are gonna bother me? Like for instance, suppose an arrival comes in this section down here, where my rank is really low. Will the arrival that arrives during this age region, will that arrival bother me? It will. It will. Okay, very confusing again. Consider arrivals anywhere in this space, okay, which includes here, okay? So consider an arrival that comes in here where my rank is really low. That arrival will come in, and because my rank is low, my rank is good, the arrival will sit. And the arrival will sit and sit and sit and sit until my rank goes up. Remember, my size is 14. So my rank will at some point go up. And the moment my rank goes up to 8, that arrival will say, I'm coming. And it moves on in. And then it gets to execute for exactly 1. Okay? So the answer to this question is all arrivals when my age is between 0 and 7, and they will bother me by 1. Okay. So the point of this slide is to introduce something that we noticed in working on this, which is when you're thinking about what kind of arrivals are going to come and bother you, you want to think not about your current rank. Okay, we don't want to consider my current rank. We want to consider my worst future rank. If my size is 1, then my worst future rank is small, okay? But if my size is 14, my worst future rank is very high. So let's look at a picture. So I call this idea the pessimism principle. And the idea is that when you're thinking about who's going to bother Jay, at every age, you want to think about Jay's worst future rank. So for instance, if Jay's size is 1, its worst future rank is this red line. If Jay's size is 6, its worst future rank looks like this. So when you consider arrivals that bother Jay, you want to just assume that Jay is running at its worst future rank, okay? Here, when Jay's size is 14, its worst future rank looks like this red line. So you want to think about this red line as the worst future rank. Okay? Why is that helpful? Suppose you're back here in the problem where we were, and you're trying to figure out who's going to bother J. Okay? You mark for yourself, this is J's worst future rank, this red line. And then you can clearly see that the arrivals that bother J are all the arrivals that happen during this region between 0 and 7. All of them bother J, because J's worst future rank is always above here. Okay, now, is this creating an upper bound on J's response time? No, this is J's exact response time. I'm computing J's exact response time because J will, by definition, go up, okay? And when it goes up, that work will get done. I may as well just pretend right from the beginning that J is always running with its worst future rank. I may as well just pretend that, okay? Because in terms of who's gonna bother me, okay, it's always going to behave like I'm running with my worst future rank. Okay, so if I want to think like who's going to bother me when I'm here, well, eventually my rank will go up to 8. So I might as well just pretend it was 8 all along, because when it goes up to 8, all those newcomers with rank 7 are going to bother me. Okay, and they're all going to give me their contribution. So this is an important principle, this pessimism principle. So in this region, everybody gets in with contribution 1. And in this region, now my worst future rank is low, so nobody's gonna bother me. So if I want to understand the mean response time for J, given it arrived into an empty system, it's a nice formula. Between ages 0 and 7, for every DA work that I want to do, every little bit of work, it creates a mini busy period. And this is 1 minus the load that bothers me. The load that bothers me is the arrivals, the arrival rate times 1. All the arrivals bother me for exactly 1 unit of time. All arrivals bother me for 1 unit of time. Between 7 and 14, it's a sum of busy periods where for every DA that I want to do, everybody bothers me for nothing. They don't bother me. Okay, they contribute 0 to me. All right. So very easy. Okay, so now let's leave our warm-up. Remember, the warm-up was J arrived into an empty system. And let's look at the more general story. So the way tag job analysis works again, there's a tag job J. I'm J, I'm your representative. And I come into the system, and for a long time I wait. And at some point I'm first served. And once I'm first served, there's some time from when I'm first served until I depart. And this whole thing here is called my response time. This is the response time for job J. It's the whole thing from when I arrive until I depart. That's my response time. Okay, so the first part is called the waiting time. This is until I'm first served. And the last part is called the residence time. This is from when I'm first served until I depart. Questions? Let's go through this residence time. Is the residence time the same as just J's service time? Is residence time the time from when J is first served until it leaves? Is that just J's service time? Please shake your head no. Okay, put your videos on because I'm going to ask a harder question. Okay, so the answer is no because there's new arrivals, obviously. Okay, but here's the harder question. Is residence time equivalent to J arriving into an empty system? Because remember, J arrives and at some point, J is first served, meaning J has the best rank. Okay, so I'm J and I have the best rank and that's why I'm about to start moving. Okay, I'm getting served. Okay, because I have the best rank. Can I just think of it as the example we just did where J arrives into an empty system? Put on your video, chat with me, talk to me. I see a no question mark. Okay, does anybody else want to say anything? Is this the same as J arrived? Like J finally has the best rank. I'm ready to go. Isn't that the same as if I just arrived into an empty system? No, it's not. Okay, and the reason is while I'm running, okay, my rank might suddenly start to go up. Okay, so I had the best rank at some point, but as I'm running, my rank goes up. And then all these jobs that I never saw before suddenly arrive and they suddenly become available. Like ghosts, they rise up from the dead, okay? So these ghosts are now here and I never saw them before, okay? But my rank went up and oh my gosh, here they are, these ghosts are here, okay? Because now they're visible because my rank is so high that they became visible. So somehow, if I want to compute residence time, I have to compute something like J arriving into an empty system plus ghosts, okay? And how in the world am I going to account for the ghosts? Okay, so I need an idea, I need a smart idea, okay, for what to do about these ghosts because I can't keep track of all the ghosts that are going to be coming up and down as I start moving, okay? So what should I do? What should J do so that J doesn't have to see ghosts? Okay, the problem is that J's rank is going to suddenly go up and then the ghosts are going to appear, right? So what I'd like to do is what? Talk to me. Yes?
Only assume your worst rank.
Perfect. I want to assume my worst rank, okay? Because then the ghosts won't come, all right? So really, I want to use the pessimism principle again. I want to assume that J has its worst rank. And what that will do is I will set the rank of J right from the beginning to be its worst rank. I will make that the rank at age 0. I'm going to set that to be the rank, okay, the worst rank, all right? And that will cause the ghosts to move, okay, because my rank is now my highest rank. And so now the time until I'm first served will move. It will scoot over. I won't get served for a while, but that's okay, okay? This will not change, okay, this will change the definition of residence time, but it will not change J's overall response time, okay? So J's overall response time is not going to change. I'm going to assume J has its worst rank here, and then of course its rank doesn't change until it gets served, okay? So here, until it gets served, it still has its worst rank, and then it's going to run with its worst rank, but none of this is going to, none of this is going to change J's response time, okay? Because this is all work that J would have had to do anyway. Anyway, J had to do this work, okay? So I'm just going to do it a little earlier, okay? But J's response time is the same. And now that I got rid of the ghosts, the residence time is the same as J arriving into an empty system, which has a beautiful formula, which we already computed, okay? So everything is very, very good, okay? So that's how we deal with residence time. Waiting time is actually an equally simple kind of idea, okay? But waiting time you already know a lot about. So J arrives into the system, it has some worst rank, okay? It basically sees some work that's relevant to it based on that worst rank, okay? And then it waits for a busy period started by that work. So waiting time, J walks in, it sees some relevant work, which I'm going to put in blue, some relevant work. And then it basically waits for a busy period started by that relevant work. That's how waiting time always works. So let's do a 1-minute analysis of all of this SERPT, okay? 1 minute. Okay, suppose the size of J is 14. So J walks in and it has some rank, some size, 14. It has some worst rank. In this case, it's 9, okay? And for waiting time, all I do is I take relevant work, which is something well known in queuing theory, and divide it by 1 minus rho, okay? And so here's a formula, and here's the answer, okay? Where I've just substituted in that the size might be 1 or 6 or 14. And for residence time, the job is now running, and we already computed this. This was the story for residence time. Between 0 and 7, I'm interrupted. Between 7 and 14, I'm not. Okay? So that's the whole story for how you analyze something like SERPT. Okay? It can sometimes get a little bit more complicated because of the relevant work being a lower number. I'll let you ask me about that afterwards because I can see I'm running out of time. Okay? So I'm going to skip through a few more slides of a little bit more complexity. Okay? But basically, bottom line, all my formulas are very, very, very simple. Okay, so we're done with SERPT, but I just want to tell you that there's so much more that can be done with this. So as I said, you can have multiple classes, each with its own rank function, okay, completely different rank function for different classes. And you can even have lexicographic ordering between the different classes, okay? So let's go back to our example. Do you remember the humans and the robots? So you have humans, they have priority 1. Robots have priority 2. Humans can't be preempted, okay? First come, first serve. Robots can be preempted, SRPT. And if the remaining size of a robot is very, very small, then we'll allow it to go ahead and preempt the human. I want to make this as complicated as I can, okay? Here is the rank function. It's a lexicographic rank function. So you look at the first entry. The first entry for a human is minus its age. The first entry for a robot is 0. What this means is if the human has started running, if its age is non-zero, if it has already started aging, then its rank will be below the robot. But if it hasn't started running yet, then they're both 0, so they're equal. In this case, the human gets a rank of X sub H, but the robot gets its remaining time, its remaining size. And if the remaining size of the robot is smaller than X sub H, then the robot wins and the robot gets to run, assuming the human's age is 0. Okay, so this is how you represent it. And you can make these arbitrarily complicated with non-preemptive and preemptive policies all mixed up. Okay, you can have like 3-dimensional, 4-dimensional rank functions. You can totally go nuts. All right, conclusion. Okay, so we talked about SOAP, and this provides an exact, closed form, simple formula for mean response time or the response time transform for lots and lots and lots of policies, including the SERPT policy, which is very important in industry, I find at least. The Gittins Index policy, which is important just because it's the theoretical optimal. Checkpoint policies, where you can only preempt jobs at certain checkpoints. And we now are writing all these papers on like, how frequently should you bother with having checkpoints because they add to the size of a job, but then you can only preempt at these checkpoints, so maybe you want to have them more frequently. So this is the kind of thing we talk about. Bucketed policies. Bucketed policies are something that I run into because I do some implementation. Sometimes when you're trying to implement something like SRPT or SERPT or something, you don't have an infinite number of priority levels. So you maybe only have like 3 priority levels in your system. Maybe you're working with a Linux kernel and it only gives you 6 priority levels. So how do you analyze a policy that switches priority in a very discrete function? This is easy to do with SOAP. Mixed classes with different scheduling policies in the different classes and all sorts of crazy stuff. We saw this. What else? So sometimes one is interested in minimizing mean slowdown. There's a policy, I call it RS, which takes into account the remaining size and the original size. And it turns out that minimizes mean slowdown. I never knew how to analyze it. Now we can analyze it. Basically, what I want is to hear from you. I want to hear about your scheduling policies And then I want to work with you on how to analyze them, or at least I wanted to make it easy for you to be able to read the paper. I'm happy to give you the slides and you can see how to do the analysis. It's all really simple. Okay, I will take questions now. I also have like slides with examples. If you want to see some examples of policies, I could talk to you about what I'm doing now in the future, whatever you want, please talk. Thank you.
Thank you, Mor. And yes, we will take questions now. And please just unmute yourself and ask.
Yes.
Great, thank you. I have two questions. The first one is actually about the contribution of the, like, I think you just went through that example where sort of the main challenge was to see which set of jobs contribute to the response time.
Yes.
And in the example seems that the, like, how much they contribute is like easy, it's just one. But I just wonder in general case, like, is it going to be much harder to just calculate how much they contribute?
So that's a good question. The other jobs, so the tag job is using its worst remaining, it's using its worst rank. The other jobs are using their actual rank function, okay? So only the tag job is using its worst rank. The other jobs are using their rank function. So what you want to do is just look at how long they're allowed to age until, like you saw in the example, until their rank becomes worse than my worst rank. So you're just looking at the rank function to judge that. So no, I don't think it's that complicated.
I see.
Okay.
And right, thank you. Second question is like, I wonder, does this analysis sort of translate to an optimization problem that can solve for the best scheduling policy, or like maybe in some subclasses what the best scheduling policy is?
I don't know. Yeah, it would be lovely if one could kind of mix this and also look at what the best scheduling policy is. I have some. So we've built on SOAP to try to mix it together with trying to look at best scheduling policies to try to understand how far away we are from the best. But in those cases, we always understood what the best was. Okay. So, so I can give you an example. Okay, so let me just skip ahead for a second. Okay, so suppose you have like an MG1, okay, and here on the other side here, I have an MGK, okay, and let's suppose the job sizes are known, okay. So now you might ask, what is the best scheduling policy? Now for the MG1, you already know the optimal scheduling policy for mean response time, it's SRPT. And it turns out it's strong, not just for MG1, it's strongest in a really, really strong sense, like it's, you know, worst case optimal and all this good kind of stuff, okay? But now you might ask yourself, well, what about for an MGK? What is the best scheduling policy? Okay. I mean, and how do we figure that out? So you might think, well, what do you think? What do you think you might want to do? Given SRPT was the right thing on the left side, what do you think you might want to do on the right side? Like
SRPT and join the shortest queue?
Yeah, but there's no queues at here. So it's just
it's KSRPT?
Yeah, so at every moment in time, I just want to run the K jobs with the shortest remaining times. So I'm going to call that SRPTK, okay? SRPTK, which at every moment in time preemptively runs the K jobs with the shortest remaining time. And the other jobs are just always put back into the queue. So preemptively, I'm always running the jobs with the shortest remaining time, okay? Now, you might ask yourself, is this optimal? This looks pretty good, okay? So we haven't figured out how to use SOAP to figure out whether something's optimal. But we do use SOAP-like analysis to be able to do the first analysis of this kind of a thing. Like normally you would think SRPTK, that sounds really, really hard. But using these kinds of ideas, these pessimism principles and stuff like that, the analysis of SRPTK is no longer so challenging, okay? Even though it's a K-server system. So what we know is it's not optimal, okay? But we can prove, for instance, we were able to get an upper bound pretty easily on the mean response time for SRPTK. And then we could show that in the limit, the mean response time under SRPTK divided by the mean response time on a single server, which is k times faster, okay, is 1, meaning that SRPTK is optimal under heavy traffic, for instance. So that's an example of something that we could build with SOAP to be able to do because we can analyze response times. I would love to be able to mix SOAP together with actually optimizing policies. That would be awesome.
Got it.
Thank you
very much.
Thank you for answering all my questions too. You're one of my question answers. Anybody else want to ask a question? I'm happy to go back to the original slide, sorry.
So in these kinds of scheduling problems, is EFT the only metric that is typically of interest? Are there other kinds of things that you might want to optimize for other than EFT?
You're asking the right person. Okay. So mean response time. So what we do is we analyze mean response time, conditional mean response time, also like conditional on the job size, and the transform of response time. But the truth of the matter is that in industry, they don't really care about mean response time so much these days. Okay, don't tell anybody, but they don't really. Okay, so what people care about is the tail of response time. So specifically, they're interested in that in a non-asymptotic sense. So what people are interested in is like, what is the probability that response time exceeds half a second? Why half a second? Because if it's less than half a second, then nobody notices because people don't notice things that are less than half a second. But if it's more than half a second, then everybody notices. I have a question coming, no? Okay, so people might be interested in finding a scheduling policy that minimizes the probability of exceeding half a second in response time. So, okay, so this is a very complicated problem, and I'm definitely doing work in this area. It's not necessarily SOAP work, but it's a hard problem. So, okay, you might think SRPT is a pretty good policy, okay? Because SRPT is very good for the mean, okay? But SRPT is not the best policy for the tail if your half a second number gets bigger, okay? So if you're looking at the probability that response time exceeds little t and t gets big, okay, then first come first serve ends up being a better policy, okay, than SRPT. Okay. And so now you might start to ask yourself, well, is it always like SRPT or first come first serve? Like, what should we do? And the answer, the truth is, I don't believe it's either of those, okay? So imagine this. Imagine your goal is to meet that half a second, okay? You want to minimize the fraction of jobs that exceed half a second. Now, when a job arrives, you could just ask, are you going to exceed half a second? Like, because I can see the queue ahead of you. Maybe the queue is first come first serve, but I can see, are you going to exceed half a second? And if you are, I'm just not even bothering to put you in the queue. I'm just going to drop you, okay? Okay. Or you could go even further. You could say, when a job arrives, if it's not going to make it, rather than drop the job, you can drop the largest job that is in the queue. Drop that one, okay? So these are policies that I know work better than the standard policies, but we don't know how to analyze them. Okay. So anyway, it's happening. It is in progress.
Okay, thanks.
If people want to work with me on something, you know, I mean, they can just let me know, or if you're already working on something and you just want thoughts, you can let me know and I will be happy to, you know, have a brainstorming session with you. Any other questions?
Well, thank you, Mor, very much for a wonderful talk and for spending the part of the afternoon with us today. Again, I apologize that we could not have done this in person. It would have been even more fun, and we'd be going out to dinner soon, but I guess we'll pass on dinner this time. We'll do it virtually. And again, many, many thanks. And hopefully we'll see you soon.
Okay, well, thank you. I'm going to send my slides and you'll see pictures there that I never got to that show you like how the scheduling policies do, you know, in case you're interested in SRPT and Gittins and things like that. You'll get to see pictures in my slides, okay, if you feel like you didn't get to see it hands-on enough. All right, thank you. See you later. Bye-bye.
Thank you.